lone pair of electrons on them, this little negative cloud of charge. And so a hydrogen ion would be attracted to that negative cloud, and it pulls a hydrogen ion. So amines are bases, they're very common bases. Also, these conjugate ions are bases. So any negative ion that's not one of the 6 strong conjugates is a base. So there's actually a lot of bases out there. Almost all negative ions are basic. They'll take a hydrogen from water. Doesn't mean that they're strong. They're not that good at it, but they can. This is a tough part of the chapter. Just wrapping your brain around the way a base behaves, writing that chemical equation with the water in it, it's going to take some practice. Here's a couple of equilibrium constants that we're going to have to know. And I think you've seen this before. If you remember anything from Chem 1, water, when it's by itself with no help at all, will automatically dissociate. Not a lot. I'm not saying not all water. I'm not saying that all water molecules will break apart, but a few of them will. And it just does this automatically, where water molecule H2O will release a hydrogen ion. You'll have hydrogen ions and hydroxide ions. Just some things about equilibrium constant. You'll remember only aqueous things and gases go into the K expression. This would be Kc. And the liquid there does not belong in the K expression. So that's why I have for the K just that product times that product, which are both aqueous. And that's it, over 1. And we don't even put the over 1 because there's nothing in the reactants that would go into the K. So hydrogen times hydroxide. And the K value is a well-documented value. It's 1 times 10 to the negative 14 is the K value. So what that tells us is that water, only to a very small amount, dissociates. Most water molecules stay together. We'll deal with this number again. This is going to come up once in a while. But other equilibrium constants, I had mentioned Ka on the previous slide. If you have an acid, this would be a weak acid, so it comes to equilibrium. And some of the molecules release hydrogen, and then you get the nitrite ion, NO2, negative 1. The K expression for this reaction would be the products over the reactants. All 3 of them are aqueous, so they all belong in the K expression. Then for bases, here's an example of a base. I just took this conjugate base from this equation and put that as a reactant down there. Remember, you need to have water as one of your reactants with bases because that base needs something to pull a hydrogen from. So the NO2 pulls a hydrogen off of water, makes HNO2. The same thing that was over there is what's made. And then the water, since it lost a hydrogen, now is the hydroxide ion. And the presence of the hydroxide ion causes this to increase the pH. Write the Kb expression. B for base, products over reactants. The water's a liquid, so it stays out. Okay. Now the next slide has something that's familiar to you, hopefully, the pH scale. We usually will have to calculate pH. In fact, if you just scan down all the exercises in chapter 14, just about all of them will at the end say, calculate the pH of the solution. You'll do something or you'll have something in water, and it's always calculate the pH. pH is calculated by taking -1 times the log of the hydrogen ion concentration. So several times so far this year we've dealt with ln, the natural log. This is, I think, the first time that we'll be able to use log base 10. And yeah, pH is a logarithmic scale. All pH does is it gives us a different way of writing what the hydrogen concentration is. In this chapter, almost all of our concentrations of hydrogen are very small, like 10 to a negative power. So when you take the log of a small number, you get a negative value. That's what that negative sign is doing out there. It makes the pH positive. That's all that negative sign is. Because, again, the concentrations of hydrogen almost universally in this chapter are small, 10 to a negative power. So the log of 10 to a negative power gives you a negative number, and that makes it positive. We can also find the POH. POH is the negative log of the hydroxide. Or, most of the time, you'll find the pH, and then you can just take the 14 minus the pH to get the POH. Because for every solution, the pH plus the POH equals 14. And that comes back from that, 10 to the negative 14. That's what that means. I know for some of you, logs are kind of an enigma still, because you haven't done it yet in your math classes. But yeah, I want you to remember pH doesn't have a unit. When you take the log of a number, you don't get a unit to it. Something else I was going to say about pH. I can't remember what it was now. It'll come back to me. All right, so the next thing that I would like to do is go through how you find the pH of a strong acid and then how you find the pH of a weak acid. For a strong acid, let's say that we have, and any of the 6 strong acids, doesn't matter which one it is, you have a 0.1 molar concentration of a strong acid. So you can dissolve like 0.1 moles of HCl in a liter of solution. That would be 0.1 molarity. Initially, before you put that acid in there, the hydrogen and the whatever the conjugate is are 0. Since this reaction goes only one way, and it goes to completion, this term right here has to go to 0. The 0.1 becomes 0. As it shifts completely to the right, this starts at 0 and it has to go up by the amount that went down, which is the whole 0.1. And that does too, goes up by 0.1. So as that goes to 0, these are going from 0 up by 0.1. And for the pH, remember pH is negative log of hydrogen ion concentration. That term right there is all we need to find the pH. At the end, what is the hydrogen ion concentration? Take the negative log of it. Now, where did that 0.1 come from? That 0.1 came from the fact that we started with 0.1 and it went to completion, right? So that's what I'm saying down here. pH is always defined as negative log of the hydrogen concentration. But since it's a strong acid, that would be the same as negative log of whatever the initial acid concentration was. That's what I'm saying there. It's very easy to find the pH of strong acids. Just take negative log of whatever the initial acid concentration was. we'll see. For weak acids, it's not so easy. It's not terrible, but it's more work. So the log of 0.1 means 10 to what power equals 0.1? That would be -1. And since we're taking negative log, we're going to take the negative of -1, so the pH of this solution would be 1. Now in the next example, we're going to see if we start with the same concentration of 0.1 molar, just like we did with the strong acid, but this is a 0.1 molar of a weak acid, HOCl. Can you tell that HOCl is a weak acid? Yes. How? Right? It's not strong. Right. There's 6 strongs to memorize. You got to know them. And then all other acids are weak. So you can see an ice table is made. In our initial line, the HOCl has been dissolved, has been measured out 0.1 molarity. Initially, the hydrogen and the ClO are at 0 because it hasn't broken apart yet. Now the fact that this acid actually has a Ka value, that kind of implies that it's weak as well. The strong acids, remember, the Ka is infinity. They completely break apart. It's all products and no reactants. But when you have, and it looks like K is a really small number too. It goes to the right a little bit and then stops. That Ka right there, I want to show you in the book how that came about. In the appendix, notice where I'm at in the book. It's way at the end. We have page A22, right at the end of the thermodynamic table. You got the delta H, delta G, delta S values. Here is another table that we'll use. Values of Ka for some monoprotic acids. Most of the problems that are given in the book, they'll give you the Ka right in the problem. But if you need a Ka, then you can look back here on page A22. In this problem, we're talking about HOCl, hypochlorous acid, it's right there. It's got a Ka value of 3.5 times 10 to the -8. I don't know if you can see the exponent. It's negative. That's how I got the Ka value there in the problem. Okay? Just look up what acid is dissociating, find it from there. Okay, well, since we have products